Welcome, everyone. Good afternoon and welcome back. Welcome to our first living room lecture of 2021. Obviously, we continue to experience an unprecedented period of time in our nation's history. We know that there is a lot vying for your time and your attention today. So we're particularly grateful you're joining us and that you continue to support this incredible collaboration of astronomers and astrophysicists at the University of California observatories. It is an absolute delight for me personally to introduce today's featured speaker, Dr. Emily Martin. I remember what must have been maybe my second week on the job here, that a faculty member brought me a stack of graduate student and postdoc profiles. Emily's was sitting on top. He brought this stack to emphasize the importance of raising the funds necessary to attract the best and the brightest young instrumentalist minds to the University of California observatories. He pointed at Emily's picture, noting that she was a rising star, pun fully intended. She was going to help change the way that we approach our work. And since I first met her in the hallways at Keck headquarters, I've absolutely agreed. Emily is currently a National Science Foundation postdoc at the University of California, Santa Cruz. And this evening, she'll be speaking to us about her recently installed instrument at Lick Observatory. Welcome, Dr. Martin.
Thank you. Thank you for having me. So it's my absolute pleasure this afternoon to tell y'all all about a brand new instrument that is coming online at Lick Observatory. And it's called PEAS, which stands for the Planet as Exoplanet Analog Spectrograph. And I'll explain all about why we wanted to build PEAS in the first place, how we actually got it built during the pandemic, and about all of the exciting science that is going to come out of it. Before I get started, I want to take a moment to acknowledge the funding sources for this project. So the NSF, the Heising-Simons Foundation, and UC Observatories. And of course, if you want to follow me on Twitter, I'm at Emily_SpaceCats because I like space and cats. So okay, and then also, there we go. Okay, also I wanted to take a minute to say thank you to all of the firefighters. It's been a couple of months since this happened, but 2020 was really a doozy of a year. And Lick Observatory came extremely close to being burnt down to the ground. And it was only because of the incredible hard work of all of the many, many people who helped save the observatory. And, you know, it was really, I really personally had it driven home driving up there in the aftermath and seeing just all of the forests that have been burned down. And even when we were over closer to the Shane Dome, you could actually see little pockets of areas that had had like embers fall on them and catch on fire that had been put out. And so everything for the most part was saved. And the major residences that were actually inhabited were saved. So just a huge, huge thank you to all of the firefighters. Okay. And also before I get into the science of everything, I just wanted to kind of set the stage for y'all so you get a little bit of perspective of my background and where I'm coming from and sort of how I got onto the path that I'm on. So I actually originally, when I was growing up in Texas, I wanted to be a professional ballerina. And until about the age of 14 or 15, that's what I really, really thought I wanted to do. And then it was actually because of a high school physics teacher that I had, Miss Antonone, who was just a huge inspiration to me. And she was the one who really showed me how much fun physics could be and completely changed my mind about science and what science is all about and just how much fun it is to do. So then I followed in the long tradition of all of my family members, and I went and I got my bachelor's degree at Texas A&M University. So that's me with my granddad, Papa. We're both Texas Aggies. And then following that, I moved out to California and I got my PhD in astronomy at UCLA. And while I was there, I had the incredible opportunity to work on an instrument project for the Keck observatories in Hawaii. So that meant that I got to go spend quite a bit of time at the summit of Mauna Kea working on this instrument project. And then after my PhD, I came to UC Santa Cruz, where I'm currently working on my postdoc. So that's where I've been for the past couple of years. Okay, so, and then broadly, what I'm interested in is connecting basically brown dwarfs, which are effectively kind of like low mass stars or exoplanets, and connecting these objects that form the way that stars form but look like planets to exoplanets, and then also connecting those to solar system planets. So it's really important to me to drive home the connections between all of those. And I both build new instruments. So this is me holding a part of the near spec upgrade for the Keck telescopes. And then I also use those instruments to take observations of brown dwarfs and exoplanets and now solar system planets. So this is kind of the broad scope of what I'm interested in and where I'm coming from. Okay, so today in the talk though, I'm going to cover first, I'm going to talk about why solar system planets themselves are excellent exoplanet laboratories. Then I'm going to cover how exactly we're going to observe these solar system planets as if they are exoplanets. Then I will get into the design and the details of PEAS, which is this new instrument that we just built for Lick Observatory. And then lastly, I'll cover the PEAS science mission and what's coming next. So let's get into it. Oh, right, and one more thing that I wanted to cover before I get into the science is every single instrument is built by a team of people. And so I really need to take a moment to acknowledge all of the many, many people who helped me on this. You know, there's a lot of people who work here in Santa Cruz at UC Observatories or up on the summit at Lick Observatory who helped out. And I also really want to take some time to highlight the students involved in the project. So Evan Morris and Julissa Villalobos are awesome students, and you will be seeing them as rising stars in the future for more instrumentation projects. Okay. So now to get us all into the context and the mindset of what we're doing, and I'm going to read a little quote from Carl Sagan because I want to start with this truly iconic photo and this quote about our pale blue dot that we call the planet Earth. So in 1990, as the Voyager 1 spacecraft was departing our solar system, it turned around for one last look at Earth. And what you see as that tiny little speck of dust, that is us here at home. And Carl Sagan said, "The Earth is a very small stage in a vast cosmic arena. Our planet is a lonely speck in the great enveloping cosmic dark." So at the time when he said those words, we hadn't yet discovered planets orbiting other stars. And yet this distant photo of Earth as a teeny tiny speck, less than a pixel across, it really makes you contemplate the very small corner of the universe that we ourselves take up. And it was actually not too long after he said those words that in 1995, the very first exoplanet around a solar type star was discovered. And as of today, there's over 4,000 confirmed exoplanets orbiting other stars. And we have thousands more that are awaiting confirmation and characterization. And now we actually know enough about exoplanets to know that there is at least one planet per every star in our galaxy. And there are billions of stars in our galaxy. And about 1 in 2 solar type stars likely has a terrestrial sized exoplanet in the habitable zone. So the idea of searching for an Earth twin is not such a crazy idea after all. Okay, so that's a little bit of context for what we're getting into. So now we have this big picture of these thousands and thousands of exoplanets that we have discovered, and we're now getting into a mode where we'd like to be able to actually characterize these exoplanets. So, you know, this is an artist's conception of what the great diversity of the various planets that we could expect to find might look like, but we do really expect there to be a huge diversity of both sizes and compositions, so whether they're rocky and like terrestrial planets or if they're gaseous or ice giants. And then also a huge variety of weather patterns that we could potentially observe in their atmospheres. And so we really would like to be able to do this in a consistent way. However, studying weather on a world that is very, very, very distant from here is actually quite challenging. And so we actually have to turn a little bit closer to home to be able to do that more consistently. But if we are able to, and when we are able to actually detect weather patterns, that can actually give us a lot of information about the physical properties of the planets themselves. So if you observe something like a big jet on the planet, that can tell you something about, for example, the way that the internal heat flux that's coming from the inside of the planet couples to the atmosphere. And so if you change the heat coupling to the atmosphere, you can get different kinds of configurations. These are theoretical models that actually a Santa Cruz professor, Shizhang, worked on. But in theory, we could take observations and compare them to the theoretical models and try to figure out things, for example, like how the heat couples to the atmosphere. But so far, we can only do this really for solar system planets, and we'd eventually like to be able to do this for exoplanets. And we do know that there is weather on all of the solar system planets. You know, there are these zonal jets that we see on Jupiter that last for quite a long time. There's also, of course, the giant red spot on Jupiter, this massive storm that is effectively 3 times the size of the Earth that has been around for centuries. On Neptune, there are these clouds that are zooming around the surface of Neptune at thousands of kilometers per hour, just like really, really fast paced storms. And on Venus, there's actually polar vortex that we've observed. And so it's pretty likely that in the huge diversity of exoplanets that exist out there, that we would see some combinations or maybe even some new kinds of weather patterns happening on their surface. And we'd like to be able to observe them. So far, we have been able to do this a little bit. And so I'm going to go over 3 of a couple of examples of weather that we have been able to observe on other worlds, but then I'm going to drive home the importance of being able to tie that back to our own solar system. So the first one that I want to cover is observations of these exoplanets that are called hot Jupiters. Now, hot Jupiters are Jupiter-sized exoplanets that actually orbit so close into their host star that their orbit is closer in than Mercury is to our own sun. And what this means is they're orbiting extremely quickly, and they're also receiving a lot of radiation from their own host star. And so because of that, they actually end up with very, very hot day sides and very, very cold night sides. And this extreme temperature difference between the night side and the day side, we've actually been able to take observations of the surface of the planet at different orientations in its orbit and confirm that indeed there is this very extreme temperature difference between the night and day sides. And that ends up driving really interesting weather patterns and likely some form of jet or like very high speed winds as the atmosphere is trying to recirculate that heat. So that's one example of exoplanet weather that we have observed. Another example actually also comes from a hot object orbiting very close to its host star. In this case, this is a super Neptune. So it's a Neptune-sized object that actually is so close to its host star that it gets really, really puffed up and is actually effectively like a Jupiter size, but the mass of it is much lower. And actually using the NIRSpec instrument that I helped upgrade on Keck, people took high-resolution spectroscopy, and they were able to show that there's actually helium escaping from the atmosphere of this object as it's basically burning off because it's so close to its host star. And so they were able to show that basically there was excess absorption coming from this tailwind of helium as it basically is zipping around its host star, which is pretty cool. And then another example that I wanted to demonstrate is actually using free-floating brown dwarfs, which are these low mass objects that are, range in mass from about 13 to 75 Jupiter masses that actually look a lot like Jupiter. And so they're about the same size and about the same makeup as Jupiter. And using this technique called Doppler imaging, scientists have been able to track spots as they rotate across the surface of a brown dwarf. And eventually we're going to get good enough at this technique and have the sensitivity in the instruments on large enough telescopes that we could eventually create these 2D weather maps of smaller exoplanets, which would be really exciting. And then a different group has used a different kind of technique to actually show that brown dwarfs are also prone to having these zonal bands, very, very similar also to the way that Jupiter does. So we're looking for, big hot spots and also zonal bands. And we think that those are two of the most common kinds of weather patterns that we would expect. Okay. So there's also been a slew of studies that have tried to look at solar system planets as if they were exoplanets. And the way that they do this is that they're trying to globally average the light from the solar system planet to study it as an exoplanet. So in the case of Carl Sagan and his team, they used the Galileo probe to take observations of the Earth. And basically what they did is they took images and they bend up the image so that it was all reduced down to one single pixel. And then they studied the colors of that, and then were able to effectively determine that, hey, Earth is blue, so it probably has a liquid ocean and made out of water. And oh, there's probably, some clouds and probably some Earth as well, some, brown colored ground. And so that was the first one that was done. That was back in 1993. And then later there was the NASA EPOXI mission, which is actually a mission to go to an asteroid. And it turned around and looked back at the Earth. And it actually was also serendipitous and caught the moon as it crossed in front of the Earth. And they also were able to show that, that the Earth does indeed show signs of life, which is exciting for us. But we'd eventually like to be able to apply these kinds of techniques to exoplanets, to say whether or not an exoplanet is one that could potentially harbor life. And then another study was carried out by Laura Mayorga using the Cassini probe that was out at Saturn, and it looked back at Jupiter. And she was able to show that basically depending on what time or what phase that Jupiter was looked at, that actually changes the observation that we see. And so it changes the color of the planet. And so what that means is that if we're looking at an exoplanet, depending on what phase we're observing it in, that might actually have a pretty significant impact on the observations that we can take. So we've taken lots of disk integrated photometry, which is imaging, but there's actually not that much disk integrated spectroscopy. And so actually the current state of the art for having globally averaged spectroscopy, so when we can look at our amount of flux as a function of wavelength, the literal state of the art is more than 20 years old. And so this was work carried out by Eric Karkoschka back in the 1990s. And he was able to use the Very Large Telescope to take these observations. And it's actually quite tricky to get globally averaged spectra of a really large object in the night sky. And I'm going to get into explaining why that is so tricky and why we wanted to build PEAS. So really this all relates to the angular size of the object on the sky. So this is 3 different objects to scale on the night sky. So the moon itself is about 1/2 degree, which is equivalent to 1800 arc seconds in the night sky. So if you try to put your moon into a spectrograph, you're only going to get a teeny tiny portion of the moon that you can look at one time. Jupiter, compared to the moon, is many times smaller from our perspective, and it's about 40 arc seconds across. It actually varies in size depending on where we are in our respective orbits, but on average, it's about 40 arc seconds. And an exoplanet system is only 2 arc seconds, which on this screen is 4 pixels across that I made it. And so if you want to compare these things, it's actually quite tricky to do. So if you wanted to compare Jupiter to an exojupiter, we're looking at vastly different scales. So Jupiter itself is 40 arc seconds across. And what that means is that we can actually spatially resolve information about the surface of Jupiter. So we can see the giant red spot, we can see the zones and the bands. But if we go look at an exoplanet system and assume that we can image the exoplanet system, in this case, it's the HR 8799 planetary system, which is one of the more famous directly imaged systems. If you go look at any single one of these planets, every single one is a single pixel. It's a single point source. And if you were to try to get spatial information out of that, you can't really, because it's not resolvable. And so what this means for if we try to take a spectrum is that if you were to use, for example, the NIRSpec instrument on Keck to try to take a spectrum, the slit size is much smaller than the actual image size of Jupiter. And there's no real way to condense the image size into a smaller slit. And what's fascinating is that if you take a spectrum of Jupiter at different locations, as this team led by Gordy Bjorker did back in 2015, the resulting spectrum varies vastly depending on where you put your slit. So if you're taking a spectrum at the pole versus at the equator, you're going to see very different looking chemical compositions. However, if you use adaptive optics and some fancy chronography and some other fancy techniques to get a spectrum of just this HR 8799c planet, what you get, you're able to get the entire planet into the slit. And so your spectrum that you measure is a perfectly globally averaged sum of everything that's going on in that atmosphere. So in the case of this particular planet, there's evidence of water and methane and carbon monoxide in the atmosphere. But so these two things are not directly comparable to each other simply because the spectra that we take from Jupiter are spatially resolved. And so that's kind of where PEAS comes in and how we want to basically put these things so that they're on the same scale to each other. And so the way that this works and the grand idea behind PEAS is that we're going to use an optic that's called an integrating sphere to spatially mix the light or the images that come from the solar system planets so that we can send globally averaged light into a spectrograph. And so the integrating sphere is a hollow sphere on the on the inside, it's got a really highly reflective surface that I actually have a little animation for. So it's a hollow sphere and there's an entrance hole. And whenever light comes in and bounces off the surface, it's actually a highly diffusive and reflective surface. And so what happens is the light scatters in all directions and it bounces around many, many, many times before it comes out of the exit port. And so the light that you get on the other side is just this really smooth, spatially mixed image. And so if you have Jupiter, for example, where you've got the bands and you've got the giant red spot, on the other side of the integrating sphere, all you're going to see is just very smooth, kind of peachy orangey light that comes out. And so we can actually feed this light to a spectrograph and then take globally averaged or disk integrated spectra of all of the solar system planets. So the basic concept for how PEAS works is it's actually a 1/2 meter telescope, and I'm going to walk through all of the various components in a lot more details, but the big overview picture is that we're using a 1/2 meter telescope and it observes the planets and it sends some of that light into an imaging camera so that we can track our objects and make sure that we're looking at putting them in the right spot, and also so that we can have simultaneous imaging. But it actually sends the bulk of the light into the integrating sphere. And so our Jupiter image or Mars or name your favorite solar system planet gets disk integrated. And then we actually have a fiber feed that connects to the integrating sphere. And the fiber optic cable sends the light into an off-the-shelf spectrograph. And then we can take spectra and then we can analyze them and do science with it. And nearly every part of PEAS is actually off the shelf, with a few exceptions. So that made it cheap and quick to build, which is nice. Okay, so now I'm going to walk you through each of the various components. Oh, right. So actually, sorry, before I do that, I'm going to give you a little bit more of a detailed zoom in of what PEAS actually looks like. So this is a CAD drawing of PEAS, and the telescope here, and then it sits on an L500 mount from PlaneWave, and then that itself sits on a rolling pier mount. So the whole thing is on this rolly cart. The whole thing weighs about 400 or 500 pounds, but I can actually wheel it around myself. It is a bit of a workout, but it is doable. And it's got these stoppers so that we can, keep it in place and don't have to worry about it rolling off while you're observing. And then the spectrograph and all of the computer and everything else that we need actually sits on the cart itself, which is quite nice. And then if we zoom in to the light path that goes through the instrument, so light mostly comes straight in through, passes through a series of beam splitters and comes into this yellow portion here, which is the integrating sphere. And there's a fiber port on the side that goes, feeds to the spectrograph. We also have light bending off into our optical imager here with room for a filter so that we can take images in different filter bands. And then we left ourselves space for if we ever do want to do an upgrade to an infrared imager. And everything rides on a motorized stage so that we can focus it every night. All right. So yeah, the telescope is a plane wave RC 20-inch telescope, which is basically a 1/2 meter, and with the fancy L500 mount from PlaneWave. So part of why we wanted this telescope, the major reason why we wanted this telescope was because their mounts are really fantastic, and they basically come out of the box ready to go. They have fantastic pointing accuracy and precision and tracking, and the software that it comes with is basically automated and ready to go. And so this is a Ritchie-Chrétien type telescope. So that means that it's a hyperbolic primary and secondary mirrors. And the effective focal length is about 3.5 meters, which means it's almost an F7 system. So this is me standing next to it for a size scale. And I think yeah, there we go. Okay, so I have a movie of basically how quickly the telescope can slew and go point to a different target. And it's just really smooth and awesome. So we've been very happy with it so far. So that's our telescope system. And the optical design itself is actually very, very simple design. So this is a ray trace diagram showing you where the light rays go in our system. So they come from infinity, they bounce off the primary, then the secondary, and then there's a series of 4 flat optics that are just sapphire windows, and they act as beam splitters and compensators. So the very first window is going to send about 10% of its light to the imager because it reflects instead of transmits. And then the rest of the light, for the most part, goes into our integrating sphere. Yeah. So this is pictures that I took as I was doing the optical assembly in the shops here at UC Observatories. So our sapphire windows are actually pretty tiny. The biggest one is only 50 millimeters across, and the smallest one is 25 millimeters. And so we designed this basically an aluminum casing for it. So each of the windows sits inside an aluminum block that was cut at a V, like 45-degree angles, and just mounted onto flat aluminum plates, and then aluminum plates that go around, and then painting to keep any reflections from other things out of our system. And then this is what our integrating sphere looks like. It's just a tiny little 1-inch sphere with a holder for the fiber port. Okay. So this is what the optical assembly looks like after it's all been put together. So all of our windows are here and the integrating sphere is on the back end. And then there's a tube here that connects, there's a filter slot for our filters and then connects to our optical camera that was also bought off the shelf. It's an S-Big. And once everything has been fully mounted on the right, I'm showing the back side of the telescope and how we mount to the back side. And everything rides on this linear stage, this motorized stage that allows us to move in and out for focusing. And so the cables you see here are basically the switches that talk to the motor and tell it what position it's in. Okay, so we have both an off-the-shelf camera and spectrograph. So the camera that we bought is an S-Big STF 8300 imager. These are really great little science quality cameras. It actually provides us with quite a large field of view. It's 17 by 13 arc minutes. And it performs quite well across the full optical. And we bought a set of UV-VRI filters so that we can observe in each of those bands, which is pretty nice. And then our spectrograph is from a company called Andor, and they make really fantastic scientific cameras as well. And then it turns out they also sell these pre-made spectrographs, which is really nice. And so we got an optical spectrograph that has 4 different gratings, so we can have different spectral ranges that we're looking at, both in terms of resolution and in terms of wavelength coverage. And the fiber actually feeds into the front end here. And then we bought a special camera that is specifically really good at doing red sensitive observations. So it's a special CCD. Yeah, so those are the off-the-shelf camera and spectrograph components. So the integrating sphere we bought from a company called Spectral Products, and it's a 1-inch sphere. And basically you want to, with integrating spheres, if you're worried about efficiency, you actually want to go smaller sphere. And so your integrating sphere efficiency goes up as the size of your sphere decreases, because you're basically increasing the density of the amount of light. And then you actually also want to keep your entrance and exit ports quite small so that you're not losing light out of those holes. And then you want to have a really high reflectance on the inside. So the inside is actually coated with this material. It's called Spectralon. I believe it's the most reflective material that we know of, which is pretty cool. It's got more than 99% reflectivity across the optical and into the infrared, which is pretty great. So that's our integrating sphere. Okay. And then our fiber assembly, we actually got lucky in that another Santa Cruz faculty member, Kevin Bundy, and one of the engineers, Nick McDonald, they both worked on the SDSS manga project, which is a fiber-fed, like massive, like many fibers that they use to collect light and study galaxies and lots of other things. And so they actually had a leftover fiber bundle that they were like, yeah, you can just have it. So that's what we're using right now. And so this is a fiber bundle. So there's lots, like every single one of these dots is its own fiber. And each one of those is 120 microns across. And then they get fed into what's called a pseudo slit. So they basically get rearranged and stacked into a single line, which is a lot more efficient for going and feeding into a spectrograph. And so we're just using one of these pseudo slits to feed our spectrograph. And so it has 32 fibers on it. And so that's what the fiber assembly looks like when it's been illuminated with laser light on the spectrograph camera itself. And so this is an image of the fibers, and you can see here how the fiber feeds into the side port of the spectrograph. And all of this is actually just sitting on top of our rolling pier mount, ready to go with P's. Okay, so we completed the assembly. So we started buying things a little more than a year ago, and did all of the design work largely right when the coronavirus pandemic started happening. And then we just kept working, and we got the telescope delivered to us back in July. And then we just kept getting more and more components delivered and started putting it together. And thankfully, by that point, the university was allowing lab workers to go back on campus. And so we were obviously wearing masks all of the time, but, you know, and limiting the number of people in each of the rooms. But I was able to actually go work at the UCO Lick lab to help put everything together. And so this is what the whole assembly looks like when it's all put together. So there's our telescope on our fancy mount, and then on the rolling pier mount. And the spectrograph sits here. And then we have a battery here so that if there are any like power surges or anything, we can keep running. And then a tiny little computer. And we also have a laptop and a monitor that run basically all of the software that we need to run to get P's to work. And this is just a different view of the whole P's assembly, but then up at Lick Observatory, so looking right as the sun set on our night for first light. Yeah, so P's traveled from Santa Cruz to Lick Observatory in mid-November of last year. And it was actually raining that day, which was a little bit scary because making those hairpin turns whenever it's raining is a little nerve-wracking. But Matt Radovan, who was driving the truck, did a fantastic job. He was very, very safe. And the guys at Lick were fantastic in terms of helping us get everything unloaded and get it all assembled. And everything went off without a hitch, which is kind of nuts. Whenever you work in instrumentation, you just kind of expect things to break. But nothing critical broke, which was really nice. And so Pease lives inside the Shane 3-meter dome up at Lick Observatory. So this is Matt, who's the main engineer on the project, myself, and Andy Skimmer, who's my faculty mentor here at Santa Cruz. And this is Pease right here sitting in front of the illuminizing tank inside the 3-meter dome. And basically it stays in there during the day. And then at night, whenever we observe, we just open the high bay door and we roll out into the parking lot and observe from there. So I have a bird's eye view of what that looks like. So this is like a Google Maps screenshot of the Shane telescope at Lick Observatory. The high bay door is just here on the eastern side. And so we roll out into the parking lot. And actually there's a nice little sweet spot that we found on our second night where the wind is a lot less. Because if you're too close to the dome, then you actually end up with wind just whipping around the dome and just turns into it being freezing cold. But yeah, so that's where Pease is going to observe from. And then every night we just wheel it back into the domes to be protected from the elements. Okay. So we achieved first light right before Thanksgiving this last year, and we actually got a spectrum of Mars, which was pretty fantastic. So this is me and Andy being very, very excited because everything actually worked on our first night. It was extremely cold that night and also very, very windy. So I'm wearing like an extra jumpsuit on top of like ski pants on top of a ski jacket. Like it was very cold. Turns out domes are there for a reason in terms of protecting you from the elements when you're observing normally, but maybe someday Pease will get an upgrade to a dome. But yeah, so we actually were able to achieve a disk integrated spectrum of Mars on our first night. And this is an equivalently long exposure of the sky, just to show you the real sensitivity that we get. And because we have a fiber bundle, we're actually getting the same spectrum of Mars in each of these fibers. So we'll be able to stack all of those spectra together so that we get even higher signal on our target. Pease had second light back in December, and then we actually haven't been up to observe again, but we probably will start observing again next week. But we had to take a bunch of calibration data, and so that involved, looking at binary systems, looking at standard stars. There was we need to make sure that we understand our wavelength calibration and make sure that we understand the throughput of the system, et cetera, before we go back to doing our science mission. But yeah, so now I'm going to walk you through a bit about what we hope to do with our first round of the Pease science mission. So the very first thing that we're going to do is produce an atlas of solar system planet spectra. So we're going to observe every single solar system planet, disk integrated, and take a spectrum and compare that to what we can do with directly imaged exoplanets. And also from those data, we're going to work with theorists here at Santa Cruz and at other institutions to compare the atmospheric compositions that we measure to what we know to be ground truth from space missions, from historical data. We have centuries of data on all of the solar system planets. We know what Jupiter is made of. We know what Mars's atmosphere is made of. We've landed rovers there, so we really actually know this. We have this in situ data that we can basically use to validate and verify that all of the techniques that we want to use on solar system or on exoplanets works on our own solar system planets. We're also going to hopefully eventually produce 2D surface maps of all of the planets and basically also validate and verify that those techniques actually work the way that they should and compare those to images that we take on the same night. And basically all of the information that we gather from this is going to help us plan future exoplanet missions. So there's the HabEx and LUVAR concepts, which are both these major NASA missions that are going to happen probably in the 2030s. There's all of the extremely large telescopes, for example, the TMT, GMT, and ELT. These are all 30-meter class telescopes that would be able to potentially take the kinds of observations on exoplanets that we're trying to do with the solar system. And everything that we learn is basically going to inform how those instruments get built. Like, what wavelength range should you be looking at? What resolving power do you need if you want to make this type of observation, et cetera. And then longer term, we'd like to track the variability in weather patterns on the solar system planets. So it's been, you know, currently right now, if I wanted to go observe Jupiter on using Keck, for example, I could go do that and maybe they'd give me one night. But to be able to go back night after night after night and to track how those weather patterns change over time, that's something that having your own dedicated telescopes means that you actually have the ability to really do that in a much more dedicated way, which is nice. And then potentially with those data, we could do something like study planetary seismology. So basically watch as the planets themselves are oscillating. So this is something that has been done, for example, with the rings of Saturn, but we could do this with other planets as well. So we're very excited about the upcoming PEACE mission. And just for a little bit of a glimpse of the timeline, so we like I mentioned earlier, we finished our design this summer and fall, and we purchased all of our hardware and got it to us over the summer and fall as well, and finally got it assembled this fall. We took it up to Lick Observatory and are currently in the commissioning phase. So that's when we are basically testing and calibrating everything to make sure that it works. And then pretty soon, like probably within the next month, we're going to start our initial solar system atlas. We're not going to be able to finish it right away because it depends on where the planets are in the night sky as to which ones you can actually observe at any time. But we'll definitely, for example, Jupiter and Saturn are going to be up in the summertime, so we're going to probably have to wait until we can get those. And then later on, starting probably at the end of this year is when we'll probably begin our time series observations. So we'll be tracking the weather patterns on a much more consistent basis. And then, of course, the whole time we're going to be also comparing our observations against atmospheric models and tweaking the models and tweaking how we understand how to do the characterization that we want to do. So that's kind of the timeline of the whole project. All right, so I'm going to do a little bit of a summary now to kind of wrap up of what I've told you about tonight. The first thing is that I told you about why solar system planets are excellent exoplanet laboratories. And that's because they're basically exoplanets that live in our backyards. They're just there. It's easy to get observations. They're bright. And we also have lots and lots of detailed information across history on all of these objects. And then I told you about how we are observing solar system planets as if they are exoplanets, and using this technique of using a special optic called an integrating sphere to smooth out the images and produce globally averaged light that we can then send into a spectrograph. I told you all about the design and details, all of the nitty-gritty instrument details of the new PEACE instrument for Lick Observatory. And then I told you a bit about our science mission and where we're going next. And yeah, so I'm just going to end it there and just say a big giant thank you to everybody who came, and I'd be very happy to take questions.
Thank you so much, Emily. We've got several different questions in the chat that I'm going to get to you, if that's okay.
Yeah.
I'm just getting here. Alec wonders, are there any effects of exoplanetary magnetic fields that could be observable from our distance?
Of exoplanetary?
Mm-hmm.
Yes, with very high resolution spectroscopy, I would imagine. Where you could, there's the technique that's basically there's an atomic splitting that can occur where you can produce a double line feature that if you had a high enough resolution spectrum, that is called Zeeman splitting, that would potentially be observable. Otherwise, I know that people have done there's actually really cool, there's some people who have been looking at aurora on brown dwarfs and basically using the radio signatures of those brown dwarfs to say whether or not they have active magnetic fields. And that is super interesting because we don't fully understand how they could support a magnetic dynamo. So that's definitely an area of active research, which is really exciting and cool.
Very cool. He also wonders what are the typical other uses for integrating spheres. He said it seems a bit ironic to have to go to the trouble of an intentionally spoiling hard-won optical resolution.
Yes. Yeah, indeed. We actually use, so it's funny because I would say most instrumentalists, when you say that you're using an integrating sphere, they're like, oh yeah, that's just like a totally normal piece of equipment. But most other people who are not instrumentalists had never heard of integrating spheres. Most often they're used in calibration units. And so what you do is you like have like a lamp source and you put it in the integrating sphere so that you can produce a very nice output that's very smooth and doesn't actually have like any image shape to it. So if you have like an arc lamp, you want to feed that into an integrating sphere before you put it into your instrument. But yeah, I agree. We're definitely working in a very opposite regime of most of astronomers where they really want the spatial resolution, and we're actually trying to do the opposite and get rid of it, which is kind of funny, but yeah.
John notes that, he's surprised that the science can be accomplished with a semi-portable scope, and says that that's so cool, right?
Thank you.
Were there challenges posed by that aspect of the design?
Yeah, and we haven't even figured out what all of them are yet. Eventually, it would be cool to get Peas its own little dome. And I would say on the whole, the fact that it is so small and portable has been part of what made us able to get it done so quickly. So that's actually mostly just been a real benefit to the project.
Yeah. We've got a couple of questions about how it's mounted and about where we do the science. John said that he was sort of surprised the telescope mount is AZ rather than equatorial, but I suppose that field rotation is not an issue for spectra.
Right. And because we're trying to disk integrate, we're not. So what basically there's two major kinds of telescope mounts for those not in the know. There's the equatorial mount, which is your much more traditional, like old school telescopes all have these equatorial mounts, and they basically run north, south, east, west. And so if you are tracking a target, you're only having to move in one of the coordinates as you do that. These altitude azimuth mounts, they actually move in 4 directions. And so as you're tracking, it's possible that your view of the sky is actually going to be rotating as you're looking at an object. But because we're not worried about the spatial aspect, and we're going to be disintegrating the whole like spatial size of a planet, then it doesn't actually matter if it's rotating while we're observing it.
There's just a basic question on, why can't we just bring it inside of a dome and observe there to avoid the wind and the cold?
We could. It would just cost more money. So we'd like to do that eventually. For sure. Yes.
Paul wonders if there are any ballpark estimates on what kind of detection limits for trace elements that you can or will achieve.
That is a really good question that I do not have the answer to yet, but I will, within actually, hopefully the next week or two, I will have an answer for you, but we're still working through the calibration.
Right. And obviously Pluto is not a planet, but will you be able to see its atmosphere? And will you
Pluto is actually probably going to be one of the harder. Even Uranus and Neptune, we are going to have a little bit more trouble because we're using such a small telescope. That's a really good question. I don't know if we're actually going to get Pluto.
Richard asks, don't you just get the spectrum of our sun when you take a spectrum of, say, Mars?
That's a really great question. So actually, when you're taking a spectrum of Mars, you're getting the reflected light from the sun. But because it's reflecting through the atmosphere, you're also getting information about Mars's atmosphere. So you do have to remove the spectrum of the sun from your observed spectrum in order to get the information about the planet itself. But yeah, that was a really great question.
John is wondering, what are some of the hypotheses you plan to test with this scope now that it's ready to go?
Yeah, so I mean, I think the major hypotheses that we're trying to test are the techniques themselves that we want to use to characterize exoplanet atmospheres. So we have these atmospheric models that start basically from first principles of physics. We put in we put in the physics that we think that we understand about how atmospheres work, but there's also likely a lot of missing physics. And so when you produce a model atmosphere that way, but you can compare it directly to an observation, then you can ask yourselves like, oh, are there aspects of this model that are missing? What are the assumptions that I'm making that are potentially wrong? Those kinds of hypotheses.
Yeah. Alex asked about why the fires didn't appear on the timeline, and obviously here, Lick specifically didn't necessarily. You weren't at Lick yet, but you were at UC Santa Cruz, where we were also evacuated for another wildfire.
The timeline did get bumped back a bit because of the fires. That's a really good point. But yeah, we were. I mean, actually, Santa Cruz was also like very, very luckily spared from burning down. I know there's some other people who work in the lab who ran up to the shops to grab some very expensive detector equipment to protect it just in case. But obviously Pease was too big for me to just throw in the back of my car. So I had to just really hope that nothing bad happened. But no, I think that, pandemic and fires aside, I've been really, really lucky that everything has gone so well.
Bruce asked, what size telescope will be needed to use this kind of technique to observe an actual exoplanet?
Probably 30-meter class, or a large, like 10 to 12 meters from space. There's probably some prime targets that we're going to be able to. There are definitely some prime targets that we'll be able to do this with the James Webb Space Telescope, which is launching later this year, because you don't have to worry about the atmosphere, which is really nice when you're observing from space. But from the ground, it's likely that if we want to do anything beyond what we've been able to do so far, we're going to require the next generation of telescopes, so the 30-meter class.
Yeah. Jorg asked, like the question, the sun spectrum reflected from Mars, aren't you getting Earth atmosphere spectrum too and need to subtract it somehow?
Yes, definitely. Yeah. So we, one of the ways that we calibrate that out is by looking at a standard star that has been very well characterized, and we're able to see the bits of the spectrum that are missing because they've been absorbed by our own Earth's atmosphere. And so then we're able to calibrate out how much of the spectrum we need to adjust because of the Earth's atmosphere. But in the optical, the major thing you have to worry about is absorption. In the infrared, you also have to worry about emission from the glowing atmosphere, which is a whole nother problem.
Yeah, absolutely. Well, thank you, Emily. If it's okay with you, we're getting towards the end of the hour, so I'm just going to wrap up a little bit here. I think that Alex Filippenko, I think you've all heard explain it best, that Lick Observatory really continues to serve as an incredibly important testing ground for technology that then goes up to the Keck telescope, which costs us $100,000 to run per night, and you don't want to be fidgeting and calibrating things there in real time without having it already tested. And then Keck will become the test bed for these 30-meter class telescopes, and in our case, the 30-meter telescope. So Pease here is a really perfect example of how the multi-campus, multi-observatory approach is really imperative to the work that we do. Her work here on Pease at Lick Observatory will ultimately prove the science behind scales. If you guys all remember hearing from Andy Schemer about his work on scales, this is testing that science and making sure that, since we'll never be able to get to these exoplanets in our lifetime, that the fundamental math and science, as the assumptions that we're making about those projects are correct. And that will then be fine-tuned to build an instrument for the 30-meter telescope. And scientists believe that it'll be that instrument that on that telescope that helps us to identify life outside of this planet for the first time. And it will have all started here with this instrument and the scientists that you just had the opportunity to hear from this afternoon. Thank you so much for joining us again for the University of California Observatory's Living Room Lecture Series. We hope to see you again real soon.